For our next trick, we're going to look at a technique that's used all over the field of AI, artificial intelligence, everything from speech processing to predictive modeling to computational linguistics. It's a simple tool that has a million applications, and it is called a Markov chain. Markov chains are just about the cutest thing you've ever seen, and I just love them to death. They are named after the brilliant Russian mathematician Andrei Markov, who is one of the smartest people ever to live, in my opinion, and one of the most underrated minds. So to understand Markov chains, we're going to have to go back and review a little bit of our probability, which you'll remember from Volume 1 of allthemath.org. And you'll remember we talked about things like the probability of a certain event. Like we might say, hey, let's choose a UMW student at random, walking down Campus Walk. What's the probability that they're female? And we might say that based on the demographics of our university, the answer is 0.65. So you remember the probability of an event is always between 0 and 1. 0 means it absolutely will not happen. 1 means it absolutely will happen, and it's scaled in between, right? So it's very intuitive here. And then we talked about the probability of something given something else. So it was the conditional probability. So what if I said, hey, we picked a random person on Campus Walk, and I'm telling you I saw an earring in one of their ears, and I couldn't see the other ear perhaps. And I'm wondering now how you might revise your prediction of whether or not you think they're female. And in this case, I think it would probably go up, because men sometimes wear earrings. And those of non-binary gender sometimes wear earrings, but it's more common among females in our culture to do that. So if you told me nothing else but that the person was wearing an earring, I'd probably revise my probability up from 0.65 to something like 0.9. On the other hand, if you said you saw this person and you could tell me they were wearing a ball cap, I would probably revise my probability down, maybe to something like 0.3 or even lower. Okay. So the point here is that we have the prior probability. You may remember that term. That's the default baseline probability of something happening given that you know no evidence about it, given that you know nothing else. And these things here are called conditional probabilities, also sometimes called posterior probabilities. And what's important to know is that they can either go up or down. That kind of messes students up sometimes, right? Especially because we learned that the probability of two events both happening, right? So we could write that like this, the probability of A intersection B, or sometimes we say, what's the probability of A and B? This is always lower than, or at the most equal to, the prior probability of A. Oops, I forgot my R's here. Okay, so and it's called the joint probability, if you remember that, right? So this always goes down. If you add other conditions here, you're never going to have a higher probability than you did before, right? What's the probability I have a female who is a geography major? That's clearly going to be less than the probability that I have a female, regardless of what their major is. However, conditional probability can go up or down, okay? This went up, this one went down. And that's just important to know. Another thing that's important to know that kind of messes up students, and this is going to come into play when we look at Markov chains, is what has to add up to 1. Okay, so suppose I said that there's a bunch of people that I'm going to test. Maybe it's the entire U.S. population that I'm going to draw from. And I'm going to say that every person in the U.S. is either a child or an adult. Those are two different things they can be. And we'll just make some hard cutoff at 18 years old or something like that. And we're also going to say that every person in the United States is either greater than 7 feet tall or higher, or they are less than 7 feet tall, okay? So every person is one of those, and every person is one of those, okay? Now, let's think this through. What if I said, hey, the probability that you are 7 feet or taller, given that you're an adult, and I said, what's the probability that you are 7 feet or taller given that you're a child? My question for you is, do these have to add up to 1? This is going to equal something, this is going to equal something. Do those have to add up to 1? And hopefully when you think through this example, which I've made kind of extreme because obviously people this tall are very, very rare, the answer is no way. They're not in the least going to add up to 1, right? The probability that you're 7 feet tall or greater given that you're an adult is probably, I don't know, I'll guess something like 0.0001. And the probability that you're 7 feet tall or higher given that you're a child is probably something like 0.000001, right? So there's probably some younger than 18 person who's 7 feet tall or greater. I'm sure that's happened in the history of the planet, but it's very, very rare, right? Even rarer than it is for adults. Okay, so these two entries are not going to add up to 1. Okay, so what is the thing that has to add up to 1? So this is what has to add up to 1. What's the probability that you're 7 feet or taller given that you're an adult? And what's the probability that you're less than 7 feet tall given that you're an adult? Okay, so these right sides match. And I'm going to say the probability that you're 7 feet tall or taller given that you're an adult is 0.001, right? That's what I estimated up here. What then is the probability that you are less than 7 feet tall given that you're an adult? Well, I can tell you right now what it is 0.999. That's the only thing that would make sense, right? These have to add up to 1. And that's because if you're an adult, you are some height. And we know that this here is a mutually exclusive, collectively exhaustive set of options. So if you're an adult, you're either going to be in the 7 foot or taller bucket, very rarely, or you're going to be in the less than 7 foot bucket, very commonly. But either way, that's going to add up to 1. Okay, so just keep in mind that these two here do not remotely have to abide by that constraint, but this other one does here. Okay, now, when we talk about Markov chains, we're going to talk about systems and states. Okay, and this is going to ring a bell from the Leslie matrix that we did a couple episodes ago. Okay, so a system is essentially any sort of, you can think of it as a complex entity that experiences changes as it goes along. Okay, we talk about dynamic systems. So a system is going to go through different states at different times. And what a Markov chain does is sort of keep track of what state a system is in at a particular time. Okay? We'll use a really simple example that everyone's familiar with, which is the weather. Okay? But this applies to anything you can think of that's a system with a state. So for instance, we might model the economy. We might say the state at any given month is the economy in recession or not? That's maybe something we could track. Okay? We might keep track of the political system in the United States, and we'd say the state at any given year is Congress controlled by Democrats or controlled by Republicans? Okay? And of course, the states don't have to be just binary like that. You could have many different things. In fact, the weather example is going to be just like that. So let's say there's 3 different weather conditions that can be present in our lovely town of Fredericksburg. We'll say that every day is either going to be sunny, cloudy, or rainy. Okay, now, obviously there are more choices than this in a real weather system. You know, there's days we have snow occasionally in Fredericksburg, and sometimes we have hail and other things. Yes, that's true. It's also true that not every day in Fredericksburg or any other location is necessarily 100% the same weather, right? So it doesn't have to be necessarily sunny or cloudy or rainy constantly from sundown to sunset. So that's all true. Or sun up to sunset, I guess. But we're going to kind of, in our simplified model here, we're going to say that that is the case. We're going to say that we do, in fact, have every day being either sunny or cloudy or rainy, full stop. Now, what if we wanted to simulate the weather in a particular location, like Fredericksburg, over some period, some sequence of days, okay, to give sort of a simulated history that turns out to be kind of a setting that applies in AI a lot? So the simplest way to think of to do that is to say, well, let's just figure out what the probabilities of each one of these are without regard to any other information, any other evidence, or any other influence or anything else, right? And I'm going to say that based on my knowledge of life in Fredericksburg, I'm going to say that if you just pick a random day and you want to know, is it going to be sunny that day? I'm going to say that happens like maybe half the time. And I'm going to say that maybe, 40% of the time there's at least partial cloud cover. And I'm going to say that 10% of the time we actually get precipitation. Okay, so you can quibble with these numbers if you live in Fredericksburg. Otherwise, just believe me. Right? Now, if I want to generate a history here, what I can do, and hopefully you remember this word from All the Math Volume 1 in the probability episode, is we can assume that the days are independent of each other. And again, independence of events means that no matter what the first one turned out to be, that has absolutely no impact one way or the other on what the other one ends up being, right? So if we were to say, for instance, that today's weather and tomorrow's weather are independent, that would mean that whether today is sunny, cloudy, or rainy has no effect on whether tomorrow is sunny, cloudy, or rainy. Okay, and we're going to revisit that in a second, but suppose we thought that. Then we can simulate this thing And by the way, those add up to 1 here. Do the mental arithmetic and convince yourself that they are equal to 1, as they must be, because these are collectively exhaustive and mutually exclusive options. I'm going to basically just have a program that picks a random number, right? Picks a random number generator, and we're going to say 0.5 of the time we're going to choose sunny, and 0.4 of the time we're going to choose cloudy, and 0.1 of the time we choose rainy. So let's say we pick our first random number, we roll the dice, and we get sunny. And then we do it again, and the next time we get rainy. And then we roll our dice again, and now we get sunny. And then we roll our dice again, and now we get cloudy. And then we roll our dice again, and now we get sunny. And then now we roll our dice again, and we get cloudy, and et cetera, et cetera, et cetera. Right, we can generate this as long as we like, right? All right, so this is our little history, and this is supposed to be somewhat representative of what weather is in Fredericksburg, especially because long-term, we're going to get the right percentage of rainy days and the right percentage of cloudy days and sunny days if we run this long enough, right? Because that's how random number generators work. Now, if you look at this, you immediately will realize the limitation here, right? And the limitation, of course, is that this just isn't true. It isn't true that 2 consecutive days have independent weather. Let me make the example even more extreme, right? Suppose I had 3 kinds of weather, and I'm just measuring the temperature now. I'm going to say that a day can either be freezing cold, in which case it's 32 degrees or lower, or it can be boiling hot, one of those horrible Fredericksburg days that's like 95% humidity and 95 degrees and da-da-da-da, it's just miserable to be around. Or it can be a mild day, which is in between, okay? Now, all those 3 happen in Fredericksburg from time to time. But I'll tell you this, I guarantee you there has never been a boiling hot day followed by a freezing day, followed by a boiling hot day in the history of Fredericksburg. I'll go on record as saying that, okay? As a matter of fact, I bet there's never been a boiling hot day followed by a freezing day, period, okay? Because if you think about it, in order to be a boiling hot day, you got to be in the middle of summer or close to it. And the only way to be a freezing day is to be in the middle of winter or close to it. So the probability that those would follow right onto each other is just nil. It's just not going to happen, right? Now, it's not quite that extreme with our example here, but I still will claim that this right here is a pretty unlikely sequence. I don't think we're normally going to be bouncing around from sunny to cloudy to sunny to cloudy to sunny to rainy, because I've noticed that the sunny days tend to come in bunches, and so do the cloudy days here. And, if the weather's kind of a little bit blah today, it probably will be for a few days before we kind of break out into a nice sunny streak, and then it'll be that way for a few days, etc., right? So what we're going to do is relax the independence assumption here, and we are going to create our first Markov chain. And this is going to be called a first-order Markov chain. I'll explain what that means in a minute. Just realize that has nothing to do with Star Wars or Supreme Leader Snoke or anything like that. First-order Markov chain has a certain property, and this is all based on conditional probability, okay? So what we're going to do is say things like this. What's the probability that what is the probability that it will be sunny on day K? So this is a subscript here. K is just a number. What's the probability that it'll be sunny on day K given that it was sunny on day K minus 1? Now, if it was sunny on day K minus 1, I'm going to say the probability that it is going to be sunny on day K is going to be maybe 0.7. Now you'll see that that's higher than I had here, right? And that's because I have new information now. I am revising my prior probability upwards in this case, because I'm going to say, a sunny day is more likely to follow on another sunny day, right? Now if I say, what's the probability that it's cloudy on day K, given that it was sunny on day K minus 1, I'm going to say that that's 0.2. And you'll notice again that that is different from this here. In fact, in this case, I've revised it downwards, right? And then I'm going to say, what's the probability that it's rainy on day K, given that it's sunny on day K minus 1? And the answer here is going to be 0.1, which happens to be the same as I have here, okay? So the conditional probability can go up, can go down, it can be the same, right? We know that that's true. Also, realize that these 3 numbers must add up to 1, okay? And that's because they all have the same right-hand side, and the left-hand sides are the full set of collectively exhaustive and mutually exclusive options. So if it was sunny on day K minus 1, it's going to be something on day K. It's not going to be 2 different somethings, and it's not going to be nothing. And that's why these numbers must add up to 1. Okay, so these are 3 conditional probabilities that I've estimated here. Now, it doesn't take a rocket scientist to see where we're going with this. We're going to make a matrix out of it. And what I'm going to do here is this. I'm going to label the rows of this matrix as day k. And I'm going to label the columns of this matrix as day k minus 1. And I'm going to label these as sunny we had first, so with that, sunny, cloudy, rainy, and I'm going to label the rows also sunny, cloudy, rainy. And I'm going to fill this up with entries. My first column is going to be this, which hopefully you remember from a moment ago when we had our 3 conditional probabilities. And that's because this thing right here means what is the probability that it's sunny on day k, given that it is sunny on day k minus 1. Because this is the sunny column for day k minus 1, and it's the sunny row for day k. Whereas this guy here represents what's the probability that it is cloudy on day k, given that it was sunny on day k minus 1, sunny the previous day, okay? Because we are in the sunny column for day k minus 1, but we are in the cloudy row for day k, right? And let me fill these in too. So again, this is just Stephen kind of based on his observations, having lived here for 15 years, but I'm going to say that's going to be 0.3, 0.6, 0.1. Cloudy days tend to follow others, as I said. And then here, I don't know if this is actually true, but I sort of feel like it's true. I feel like once it rains, it's sort of gotten the rain out of its system for a while. I don't feel like it rains consecutive days here much. Seems like once it rains one day, it's more likely to be sunny or cloudy the day after that and not continue to rain. And so this right here actually is the lowest of the 3 rain entries here, right? All right, now, this here, I'm going to label this W for weather. Okay, that's our matrix here. And this matrix has a special property. And, I mentioned that there are things in computer science that have lots of different names, and that they're super important and widely used when they have multiple different names. This kind of matrix has, I kid you not 2, not 3, not 4, but 5 different names. It is called, by some people, a Markov matrix. Other people prefer the term probability matrix. Some people prefer the term substitution matrix. Some prefer the term transition matrix, which is actually the one that I think makes the most sense, because really what this is giving us is the probabilities for transitioning from one state to another. That's not actually the one I usually use, though. I usually use this one because it sounds the coolest, okay? Stochastic matrix is the name I use for this, okay? All these terms mean exactly the same thing. By the way, stochastic, I may have mentioned in all the Math Volume 1, is another word for probabilistic or non-deterministic. So anytime you're dealing with probabilities, you can't determine for sure what's going to happen, but there's, some range of outcomes that might happen. You're dealing with a stochastic system, right? So here are the rules for a stochastic matrix. Number 1, all entries must be between 0 and 1. And you'll agree, I think, when you look at this, that satisfies that condition. And that's because all these are probabilities, right? It wouldn't make sense to say the probability of it being cloudy on day k, given that it was raining on day k minus 1, is 1.3, because that's not even a probability, right? And it wouldn't make sense to be negative, because that's not a probability. So all the entries must be between 0 and 1. And then, importantly, all the columns, not rows, columns must add up to 1. And realize why that is, okay? There's no reason that the rows should add up to 1. Just like there's no reason that the probability that you are over 7 feet tall given that you're a child and the probability that you're over 7 feet tall given that you're an adult should add up to 1. That's going to add up to way less than 1 because there just aren't that many 7 feet tall people. Similarly here, we get a lot of sunny days in Fredericksburg. That row is not going to add up to 1. We don't get much rain compared to other places here, right? So that's not going to add up to 1 either. None of the rows are going to add up to 1. But the columns must. And that's because given that it was, say, cloudy on day k minus 1, one and only one thing is going to happen the next day. Not 2 different things, not nothing, but exactly one thing, therefore these must add up to 1, okay? So any matrix where those 2 things are true is called a stochastic matrix, or a transition matrix, or a substitution matrix, or a probability matrix, or a Markov matrix, okay? You may remember from a couple episodes ago the Leslie matrix, okay? Not the same thing, but we also had certain conditions on it, right? We had certain entries that had to be equal to 0 and certain things that had to be between 0 and 1, all that kind of stuff, right? Okay, now here's the way a Markov matrix works. Let's make a vector called day 1, and I'm going to make it equal to 1, 0, 0, right? Now, the name for this is often called the initial condition. And this basically says that when our system kicks off, when it gets going, it is going to be in a certain state to start with. And I have chosen us to start in the sunny state. 1, 0, 0 basically means there is a 100% chance that day 1 was sunny. And there's a 0% chance that day 1 was cloudy or rainy, okay? So this particular one, we know to 100% accuracy, we know exactly what happened that day, okay? Now what we're going to do in predictive analytics fashion is we're going to start to be a weatherman, right? We're going to try to forecast what's going to happen in the future. So we're going to say, well, what's going to happen on day 2? And the answer is simply this. Boom. Just like the Leslie matrix, right? We had our population vector here, remember, for a particular year or whatever the unit of time was. We multiplied that by our Leslie matrix, and we got the corresponding vector of populations for the next time period. Exactly the same thing is happening here, okay? So let me put W back up here just so we remember it. It was 0.7, 0.2, 0.1, it was 0.3, 0.6, 0.1, and it was 0.4, 0.55, 0.05. So I think in your head, you could multiply this by 1, 0, 0. And I think that you would realize that you would say day 2 is going to be equal to the vector 0.7, 0.2, 0.1, right? Because that's just a straightforward. We want one copy of the first column, no copies of the second column, no copies of the third column. Add them all up together, we get 0.7, 0.2, 0.1, okay? Now, this does not mean that day 2 is going to be 70% sunny and 20% cloudy and 10% rainy, okay? It's not what it means. What it means is there's a 70% chance that it's going to be 100% sunny. And there's a 20% chance it's going to be all cloudy. And there's a 10% chance that it's going to be all rainy. So we're looking into the future here, and because we're looking into the uncertain future, we're not going to get a vector like this where all of the probability mass is all on one option. We're going to get something that looks like this where we have to kind of hedge our bets, right? But what we're saying here is that if day 1 is sunny, then day 2 is more likely to be sunny than the other options because that's what that column looks like. Okay. Now, what is the weather going to look like on day 3? And you can see where I'm going with this. That is going to be W times day 2 because all we do is run it forward one more day. This, of course, is W times day 1, right? Because that's what we did right here. This is how we got day 2. And if we work that out, that's not going to be one you can do in your head because now we're going to say I want 0.7 of the first column plus 0.2 of the second column plus 0.1 of the third column. That's not math I can do in my head, but we're going to come out with some answer. And that answer is going to be a vector. And I can tell you right now that all of the entries are going to be between 0 and 1. And I can tell you right now they're going to add up to 1 because that's just how this works. And in general, if I want to know what day n's weather is going to be, that is going to be W to the n times day 1. We're going to multiply W times itself n times and multiply it by the day 1 vector. Now you might say, well gosh, don't I want to multiply W times day 1 first and then multiply W by that and then multiply W by that, etc.? Do I really want to multiply all the W's beforehand by each other first before I multiply by the initial condition? And the answer doesn't matter. Because remember that matrix multiplication is associative. And associative means it doesn't matter what order you do the operations in a sequence of multiplications. So we can simply take W and take it to a power and then multiply it by our initial condition. Okay? So that's what a Markov chain is, and it's super cool. Now, you're going to ask me, Stephen, what does this have to do with eigenvalues and eigenvectors? I'm glad you asked. Okay? Because here's the deal. suppose I have modeled those probabilities meticulously, and I've figured out, in our case, we have reason to believe that, cloudy days are going to lead to other cloudy days with a certain probability, and sunny days are going to follow upon rainy days with a certain probability because we've studied the weather system and this, that, and the other thing, blah, 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 blah. And now we have our Markov matrix here, okay? Oh, and by the way, I forgot to explain why it's a first-order Markov matrix. It's a first-order Markov chain because each day depends only on the immediately previous day. So if we get a cloudy day, and then following upon that is a rainy day, the next day only depends on the fact that this day was rainy. The system does not look any further into the past to see, it was a cloudy, rainy sequence. Now what's the third day likely to be, given that it was a cloudy, rainy sequence? If you do that, it is called, no surprise, a second-order Markov chain. And it's a little bit more complicated because it's not just one single matrix like that, right? But you can have a Markov chain that looks back any number of steps. Very often, though, you get a lot of mileage out of just a first-order Markov chain where you look back at just one step, okay? Now, eigenvectors. Would you believe that if I wanted to know the long-term probability of sunny, rainy, and cloudy days, period, if I wanted to know, hey, what's the weather going to be like in Fredericksburg on a given day, given that matrix, the answer turns out to be, wait for it, the dominant eigenvector. Whoa, really? Yeah. And the reason it's like that is, you may remember from last episode, how there's a magnetic pull. Remember this diagram that we did? I said, let's say we have a matrix here, and we're going to multiply, some vector, who knows what it is, times a matrix. And I plotted on this thing the dominant eigenvector, right? And you'll remember that when we multiplied the matrix by this, it got converted to some other vector. And if we fed that vector back into the thing, it got converted to some other vector. And lo and behold, we saw sort of the amazing property that as you continue to multiply that matrix by itself a million zillion times, it cruises right to the dominant eigenvector's direction. It's amazing how that works. But that's what happens. Let's say our matrix is called A. If you multiply A times X, let's say this first vector right there was X, right? And then multiply that thing by A, 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 and keep going like that. You eventually get to the dominant eigenvector. The only way you're not is if X happens to start off exactly in the direction of one of the other eigenvectors. Then that doesn't happen, right? But the vast majority of the time, that's exactly what happens, okay? Now think about it. That's exactly what we have with this Markov chain, right? We started with day 1, and we multiplied that by W to get day 2, and we multiplied that by W to get day 3, and multiplied that by W to get day 4, and we multiplied that by W to get 5, blah, 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 blah. Now, granted, our day vector was not two-dimensional like this X was here, like maybe, we're at 2, 1 or something, I don't know. Let's say that's the point 2, 1 right there. Here, our day vector is 3 dimensions, and in general, if we have, 20 different states, we're going to have 20 different directions, and we'll have a 20-dimensional vector. But nevertheless, this whole thing still applies. It's going to be pulled in the direction of the dominant eigenvector in 3-dimensional space for our rainy, cloudy, sunny example. Or in 10-dimensional space if there's 10 different states that I'm modeling, right? Or 100 different states or whatever. It's exactly the same property. It's going to get dragged to the eigenvector that is dominant. So all we need to do, it turns out, once we have our Markov chain modeled, is ask Python, hey Python, what are the eigenvectors of this thing? Give me the dominant one. And that thing is going to tell me long-term what percentage of the time I'm going to be in a rainy day, I'm going to be in a cloudy day, I'm going to be in a sunny day. And it's precisely because of that magnetic pull thing that it's doing. Okay? Amazing. That is unlocking the secrets of the Markov chain. All right? Let's do an example here in Python. So Python here, I've got this vector, or this matrix W, right? I've made the very one that we did. So let's just, run that thing. Oh, I guess I need to just call array, not NP array. Here's our Markov matrix here, right? Or our stochastic matrix, whatever you want to call it. And you'll see that all of the columns add up to 1. And all I'm going to do here is say, let's do the linalg.eig thing, We're going to do linalg.eig of w, and we're going to save that to eigenstuff. And if we look at that, we're going to say, hey, what is eigenstuff anyway? And it's going to say, oh, it's this crazy looking matrix here. By the way, you will notice that the dominant eigenvalue is 1. Fun fact, the dominant eigenvalue of every Markov matrix, every stochastic matrix, every transition matrix is 1. Turns out that if all of the columns add up to 1 like that, and all the entries are between 0 and 1, you're guaranteed to have a 1 eigenvalue. Kind of a useful fact to know. All right, so what we're going to do here is we're going to get the dominant eigenvector. I'll call it dom eigv. That is going to be eigenstuff of 1. Remember, entry 0 gives us the eigenvalues. Entry 1 gives us the eigenvectors. And then we're going to take, of that matrix, all of the rows, and we're going to take only column 0, please. Right? So if we run this thing and we say, what is the dominant eigenvector? We get, oops. I forgot my comma here. We get this thing, right? Now, you're looking at this saying, whoa, what do you mean probabilities? These are like negative, okay? Well, remember that the eigenvector we get back is just a vector that is pointing in the same direction as all of the eigenvectors do, right? So all we've got here is the direction. If we actually want to know the probabilities, what we need to do is very simple. We just divide by the sum of the entries. If you divide by the sum of the entries, that is going to make them all add up to 1. And when we do that, we get this. 0.5158, 0.3889, 0.0952. Those are the dominant, those are the entries of the dominant eigenvector normalized to add up to 1. And so this tells us that with this Markov chain, if you run this thing forever, you are going to get, on average, 52% sunny days, 39% cloudy days, and 0.095% rainy days. That's kind of amazing we can figure that out, right? Because you look into the future and you're like, okay, well, there's, 70% chance I go here and a 20% chance I go here and a 10% chance I go here. Okay, now if I go 70% here, well, then there's a 30% chance that this happens and a 20% chance that it happens. Oh, but if I went here, then it's a 40% chance this happens and a 20% chance that it happens. I mean, how in the world could you possibly hold all that in your head to compute all the way to eternity and say, now we know that as the weather goes back and forth between these states, 51.5% of the time it's going to be in this particular state. But that's the magic of what eigenvectors do. They sort of do that infinite calculation for you and come back and give you the right answer. Okay, so that's how this whole thing can be made to work. Now I got another example for you here, and let me change domains here. I'm going to change to basketball for a second. All right. So I've watched a lot of basketball games in my life. And I'm going to say that a particular basketball team has 4 outcomes they could have for a particular game. Okay. And I'm going to call them win plus, win, loss, and loss minus. So this is where the basketball team wins a close game. And this is where the basketball team loses a close game. W plus means a blowout win for the team you're following, and L minus means a crushing loss. You lost by 30 points or something like that, right? So in true Markovian fashion here, I'm going to label these things W plus, W, L, and L minus. Here I'm going to name them W plus, W, L, and L minus. And this represents here, game K minus 1, and this represents game K. And the reason that a Markov chain is useful here, I claim, is because there's sort of some memory that a team has, right? I don't know if it's sort of the emotional roller coaster of the season or your confidence level or whatever, but there's definitely this idea that you can kind of get on a hot streak or get on a cold streak or whatever, right? That definitely is something that I've noticed. So I'm going to sort of make up something that I think I've observed about basketball teams. I'm going to say that if you have a blowout win some game, you're actually not going to have a blowout win the next game. It always seems like teams that have a really easy win, they cruise to an easy win, inevitably the next game is close. They might end up winning it. I'm going to say that happens half the time. They might end up losing it. I'm going to say that happens the other half of the time. But the next game is almost always close. It's weird. You don't end up just continually having blowout wins. I think because you get overconfident and you sort of think, oh, the next game we can kind of mail it in because we really crushed this one, right? Now, what happens if you win the next game? Just win a normal amount. You won by 3 or 4 points or whatever. I'm going to say that carries some momentum with it. There's sort of a 60% chance you're going to win the next game. There's also a 20% chance that you're going to have so much momentum that you go into a blowout win scenario. And there's going to be a 0.1 chance for these other things here, right? So, keep me honest here that all these columns add up to 1. I'm going to say if you lose a game, that too has momentum. You're going to have kind of a 50% chance of staying on that losing streak. In fact, there's a 0.1 chance that you're even going to drop down into a blowout loss. And we're going to say you have a 0.4 chance of popping into the win columns. You can break out of your losing streak, but that's actually less likely than it is to stay in your losing streak. And then if you get crushed, man, those tend to accumulate. There's a 30% chance you're going to stay in a series of blowout losses. There's a 40% chance you're going to make a comeback and at least make it close. But there's only a 30% chance that you're going to end up popping into the win column again. All right. So let's say this is what your basketball team is doing, right? Now I ask you, what's the winning percentage going to be for this team? I start them off in a particular game, the beginning of the season, and I simulate it with all these transition probabilities. Is this going to be a winning season or a losing season, and by how much? And by the way, notice one very interesting property of Markov chains. Notice that when we figured out the answer to this question for the weather example, what we did was we figured out, I'm going to call this B for basketball, right? We figured out the eigenvector, the dominant eigenvector of B. That was the answer to the question here, right? The dominant eigenvector of W for the weather case or B for the basketball case. Notice that the initial condition doesn't even play into it. It's kind of a deep thought if you think about it for a minute, right? If we run this Markov chain for a while, turns out it doesn't even matter where we started. It doesn't matter if we started with a rainy day, sunny day, or cloudy day. It doesn't matter if we started with a win or a loss and whether it was, by how much. Those things eventually don't matter, and that's because as the Markov chain runs, your initial condition is getting further and further in the past, right? And so pretty soon, it doesn't even matter what you started with. The Markov chain is all warmed up, and it's all kind of in its wheelhouse of properties. And therefore, there isn't any point in really knowing what the initial condition is. That's why figuring out what the long-term distribution of states is going to be has nothing to do with the initial condition. Here's another way to think of it, right? If I said, hey, how likely is it to be cloudy this weekend? And I'm asking you this on Wednesday. You can factor in your Wednesday information a little bit to know that, right? Because Wednesday's close enough to the weekend that there's some influence there. But what if I asked you, hey, you're going to plan your wedding for next summer, say, right? Your wedding's, 9 months off. What's the best day to plan it on? Should I plan it, June 15th, or should I wait for June 22nd? Which day is more likely to be rainy? It's not going to tell you anything, right? You can't get any information about what the future is going to be based on what it is a year earlier, because by that time, the diminishing influence of the initial condition has already petered out. And the only thing that's going to matter is the Markov matrix itself, which gives you those transition probabilities. All right, let's get back to our basketball game and just real quick figure out what the answer is. So in this other window, I have made the other matrix here. And I'll take off my NP because I didn't do that before, right? So here is my transition matrix for the basketball team. And again, all I'm going to do is say, let's get lin algebra dot eig. And I'm going to say, take that of B. And I'll just do this all in one line here. I'm going to say, let's get element number 1, which is the eigenvectors, not the eigenvalues. And then let me get only the first column of it, right? And I'll save that as to dom eig. And then let's just say dom eig divided by the sum of the entries to normalize it to 1. I will print out that bad boy. And it turns out that this is our long-term performance here. We are going to get about 10% blowout wins. We're going to get about 50% close wins. We're going to get about 29% close losses. We're going to get about 11% blowout losses, right? So if I assigned this to a variable, and I called it long term, and I set it equal to that. And I said, hey, what's my winning percentage going to be? Well, it's going to be long-term element 0 plus long-term element 1, right? That's going to be 60% wins, whether or not they are blowout wins or whether or not they are close wins, right? So as long as you can model some system as having a state that is influenced by its preceding state and only by its preceding state, which turns out to be a good approximation for a lot of stuff, you can end up using eigenvalues and eigenvectors to do predictive analytics on that. It's used a lot of things, for instance, in speech recognition, or your autocorrect on your phone. You may have noticed that when you type something and you get like a word wrong, it like auto-suggests certain things, right? Now your phone is smart. It's looking at what you typed and it's saying, okay, they typed something which isn't a real word, so what words are kind of close to that, what words are like one letter off or something. It takes that into account, but it also looks at the previous word you just typed. And it said, what word would make sense coming after that, right? So if there's some, common phrase, like let's say barbecue picnic, right? If you type barbecue and then you type picnic and you spell it with a K, right? P-I-K, it could say, well, maybe they meant picnic, P-I-C-N-I-C, but maybe they meant pikes, because that's a word too, right? Or maybe they meant pickle. I mean, there's a lot of words that are close to that. But when it sees the word barbecue before it, it says, what's the probability that they would have said barbecue pikes? That's not very likely. What's the probability they would say barbecue pickle? Maybe that's a thing. I don't know. But barbecue picnic is far more likely, right? So what it's using there is a Markov chain, where it basically says, every single word they might have typed is essentially a row and a column in this giant vector, and we're going to be able to predict what the words are based on that. Markov chains, powerful technique used all over artificial intelligence.